All right, let's get started in our first lecture of Math 66 Calculus 2 with a discussion of the area between two curves, finding the area between two curves. So this is section 6.1 of Anton's calculus. Okay, so first of all, just as a reminder, and this is something that you would have talked about back in Calc 1, all right? But the integral from a to b of f of x dx gives the net signed area between f of x and the x-axis over the interval a, b. And so here's a picture, right? So you're finding the area under the curve, between the curve and the x-axis over this interval. That's what this integral is. This integral, though, is the net signed area. And what we mean by that is that it's not necessarily the total area under the curve, because anytime the function dips below the x-axis, then the area that's underneath the x-axis is going to be assigned a negative value. And so you don't actually get the full total area, right? So, so imagine that you have this kind of function where you're dipping below the x-axis, then you go above it, and then below it, and then above it again, and you integrate from a to b. What you're going to get we call the net signed area, right? So the net signed area is the integral from a to b of f of x dx. The total area, if you wanted to find the total area, now if you just integrate from a to L, you're going to get a negative value. And so if you want to find the actual area, then you need to negate that negative value to make it a positive value. So from a to L, we negate the integral. Then from L to M, this is going to be a positive value, so we keep it positive. From M to N, it's going to be a negative value, so we negate it so that it becomes positive. And then from N to B, we keep it positive again. And so this would actually be the total area. So you actually have to split the integral every time you cross the x-axis, and then negate anything below the x-axis in order to get the actual area. Okay, so the integral is the net signed area. So that's just review of stuff that you should have seen in Calc 1. Now, what we're going to do in this section is we're going to try to find the area between two curves. So instead of trying to find the area between a curve and the x-axis, we're going to try to find the area between two curves. And the good news is that it's pretty simple to do that, right? So if we want to find the area between two curves, we just subtract the bottom area from the top area. And so here's a picture. So imagine that you've got these two functions, f of x, g of x, and that you're interested in finding the area between those two curves over the interval from a to b. Well, we could find the area under the curve, between the curve of f of x and the x-axis over the interval from a to b, just by integrating, right? We just integrate from a to b f of x dx. And that's going to give us, that'll give us this entire area, right? It'll give us this entire area going all the way down to the x-axis, right? It'll give us all of that. But we weren't interested in this bottom part, so how do we get rid of it? Well, if we integrate g of x, the bottom function, from a to b, notice that that's going to give us this bottom part. That'll give us this bottom part down here. And so what we can do is find the integral, or find the area under f of x by integrating f of x from a to b, and then find the integral, or find the area under g of x by calculating the integral of g of x from a to b, and then we just subtract this part off, right? We just get rid of this, right? We just subtract it off. And so that's exactly what we're doing here. We're just taking the top function, subtracting the bottom function, and then integrating from a to b. So that's how you find the area between two curves. And if you think about this, it works out in any situation. So even if you have like a situation where g of x dips below the x-axis or something like this, right? It still works that the area between these two curves is just the integral from a to b of the top one minus the bottom one. Because again, anything below the x-axis is going to get a negative value, right? So, if you were to calculate just the integral from a to b of f of x, just f of x, that's going to give you all of this top stuff, right? It's going to give you all of the top stuff above the x-axis. And then if you integrate from a to b just g of x, then it's going to give you all of this bottom stuff, but it's going to give it to you as a negative value, right? It's going to give this as a negative value. So when you subtract, a negative value becomes a positive value, and so sure enough, you get this total area, right, between these two curves. Now at this point, I don't know, we could call this point C or something like that. But at this point, g of x suddenly becomes positive again, which is good because then when you subtract off g of x, you'll be subtracting off this stuff down here, which you want to subtract off because you weren't interested in this stuff, right? You're subtracting it off. So anyway, the moral of the story is this still works, right? This still gives you the area between the two curves. So even if your functions are dipping, below the x-axis, it still works out. Another scenario that you might encounter with these types of problems is you could have a place where the functions cross. So maybe you start off with a scenario like this where f of x is on top and g of x is on bottom. And so then to find the area between the curves, of course, you just do f of x minus g of x. But then at this point, which I'm calling C, the functions cross and they swap places, and g of x ends up on top and f of x ends up on bottom. Well, so then you have to split your integral, right? You're not just going to integrate from a to b f of x minus g of x. You have to split it wherever they cross and go from a to c, f of x minus g of x, and then from c to b, g of x minus f of x. So the moral of the story is just make sure that you're subtracting the top function. Make sure you're subtracting the bottom function from the top function. So it should be top function minus bottom function. Okay? And anywhere where they cross and swap places, you have to split your integral. Okay? So that you can change the order of the subtraction. Okay. So let's look at some problems. Give me a second. Sorry, my family is downstairs. I guess they decided to have like a dance party or something because they're just rocking out to some music. I had to tell them to turn it down. Anyway, but let's look at this first example now. So it says, so we're supposed to find the area of the region bounded above by y equals x plus 6 and below by y equals x squared, and on the sides by x equals 0 and x equals 2. Okay, well, so a good thing to do with problems like this is to draw a picture. So, I mean, you should draw a picture, anytime you're doing a problem like this, I would say drawing a picture is a good thing to do. So, so we've got a region. It's bounded on the sides by x equals 0 and x equals 2. Okay, so that's as far as I need to go along the x-axis. And it's bounded above by y equals x plus 6. Okay, 1, 2, 3. Oh, I should have made this 4, 5, 6. I should have, I might have to redraw this. Okay. 1, 2, 3, 4, 5, 6. 1, 2. And x plus 6. Okay, so it starts there, and then we're going to go up 1, over 1, up 1, over 1. So there's that line. And then we have the parabola, y equals x squared. So that's going to look like this, and then 1, 2, 1, 2, 3, 4. And of course, I mean, that keeps going, right? Keeps going in both directions, but we're only interested in integrating from 0 to 2. So, so this is the region that we must be talking about, right? X equals 0, x equals 2, and then it's the region between these two curves. So this is what this is the area that we're trying to find. Okay, so this is y equals x plus 6. This is y equals x squared. This should be pretty easy then, right? So the area is just going to be x plus 6 minus x squared, right? Integral from 0 to 2. Okay. So integral from 0 to 2 of x plus 6 minus x squared dx. Okay. So the rest is history, right? The rest is pretty straightforward, I would say. So let's integrate this, right? We're going to say, well, this equals, I'm just going to clean it up a little bit, write it in descending order. We've got 0 to 2, negative x squared plus x plus 6 dx. And then we can just use the power rule for each of those things. So this is going to be negative x cubed over 3 plus x squared over 2 plus 6x evaluated from 0 to 2. Okay, so then if we plug in 2 cubed is 8, right? So we get negative 8 thirds plus 2 squared is 4. 4 divided by 2 is 2. And then 6 times 2 is 12. Okay, so we get this minus, when we plug in 0, we're going to get 0 everywhere, right? 0 plus 0 plus 0. Okay, and that's that. So 12 plus 2 is 14. 14 times 3 is 42. 42 minus 8 is 34, so I guess we get 34 thirds. Okay, check my arithmetic on that, but I think that's what you should end up with, is 34 thirds. The main thing is I want to make sure you can set up the problem, draw the picture, right? Set up the problem, and then integrate correctly, of course. But I sometimes make mistakes with arithmetic, right? Okay, so there's that example. Let's look at another one. So this next one says, find the area of the region enclosed between y equals x squared and y equals x plus 6. Well, same functions as before, but this time it's not bounded on the sides by 0 and 2. So we're going to have to do some work to figure out where these curves intersect so that we know where to integrate between. So let's again draw a picture. Okay, so if I want to know where the curves, so I've got y equals x plus 6 and then y equals x squared. If I want to know where those two curves intersect, I can just set the functions equal to one another, right? So I can just say, well, where does x squared equal x plus 6? So that's going to give us x squared minus x minus 6 equals 0. Which, isn't this nice? It factors so nicely. So x minus 3, x plus 2. And so that means x equals 3 or x equals negative 2. So those are the two places where the functions are going to intersect. So it looks like we're going to integrate between negative 2 and 3. You actually probably don't even need to draw a picture at this point because you know that this is where the functions are going to intersect. I'm just going to draw one anyway, though, for the sake of completeness, I suppose. So at negative 2 and at 3, the things intersect. 1, 2, 3, 4, 5, 6. And then you're going to go up 3 over 3. For the line, you'd go down 2 and over 2. So there's our straight line. And as for the parabola, right, 0, 0, negative 1, 1, 1, 1, negative 2, 4, 1, 2, 3, 4. Oh, yep, sure enough, they cross right there. 2, 4, and then 3, 9, right? So this is the picture, and this is the area that we are wanting to find. So it's going to be the integral from negative 2 to 3 of top function minus bottom function, right? So x plus 6 minus x squared. So same integral as before, but different limits of integration. So negative x squared plus x plus 6. So that's negative x cubed over 3 plus x squared over 2 plus 6x from negative 2 to 3. And we did the first part already, plugging in... Oh, no, actually we didn't. Sorry. So plugging in 3 cubed, 3 times 3 is 9, so 3 is 27. 27 divided by 3 is 9, though. We get negative 9. 3 squared is 9, divided by 2 is just, I guess, 9 halves. And then 6 times 3 is 18. When we plug in negative 2 cubed is negative 8. This negative makes it a positive 8, so it'll be 8 thirds. Negative 2 squared is 4. 4 divided by 2 is 2. And negative 2 times 6 is negative 12. And I'm just going to pop this into my calculator at this point. Well, I can do some of it in my head, I guess. Negative 9 plus 18 is 9. 9 is 18 halves, and 18 halves plus 9 halves would be 27 halves, right? So we're going to hit 27 over 2. And then let's see. 2 minus 12 is negative 10. Negative 10 is negative 30 thirds. Negative 30 thirds plus 8 thirds would be negative 22 thirds. Negative and a negative make it a positive, so we're going to get plus 22 thirds. Again, check my arithmetic, but I think that should be right. Yeah, I think that's right. Negative 9. I'm checking in my calculator. I just did all that work in my head just to check into my calculator, but no, that's correct. Okay, so 27 halves plus 22 thirds is 125 over 6. Okay, and that's that one. Okay. Now, sometimes it's useful to integrate with respect to y rather than with respect to x. When we integrate with respect to y, we're finding the net signed area between the curve and the y-axis. So it's like everything gets sort of tipped over, you might say. So your limits of integration are going to be along the y-axis now instead of being along the x-axis. But this area is the integral from a to b of f of y dy. So your function needs to be given in terms of y, and if it's not, then you need to solve it so that it's that way. And then your limits of integration need to be along the y-axis, right? But this will give this area just like it did for, if you were integrating with respect to x. So let's practice that a little bit. So third example, find the area of the region enclosed by x equals y squared and y equals x minus 2 by integrating with respect to x and then with respect to y. So we'll do it both ways so that we can kind of see how this goes. So I have a feeling we're going to, for me, it's just helpful to see what's going on. So I'm going to draw, again, I'm going to draw the graphs. So x equals y squared. So we have x equals y squared and y equals x minus 2. Okay. So when it comes to drawing these things, x equals y squared, that's a parabola that's been tipped over on its side, right? So it's opening up on its side. And then y equals x minus 2. We're just supposed to find the area of the region enclosed by these curves. So let's see. Okay, so y equals x squared is going to look like this. 4. So it's going to look kind of like this. Oh, missed it. And then y equals x minus 2. We're going to start here. We're going to go up 1, over 1. Oh, so we cross pretty suddenly. Up 1, over 1, up 1, over 1, up 1, over 1. We cross right there again. So y equals x minus 2 looks something like that. So we're wanting to find the area enclosed by these curves. So that's this area right here. Right? So that's the area that we're trying to find. Okay, so for part A, with respect to x, so we're going to try to do this sort of in the traditional way. So doing this with respect to x, definitely from so from 1 to 2, 3, 4. So from 1 to 4, we can definitely just integrate from. We can definitely just do this function minus that function. So we can integrate from 1 to 4, this function minus that function, and that'll give us this kind of right side. It's the left side that's kind of messing with me a little bit. But here's what I think. I think what I can do is the problem is that I've got this function. It's the same function on top and bottom, right? But if I think in order to integrate with respect to x, I'm going to need to rewrite this parabola. I'm going to need to solve for y so that I'm getting the function in terms of x, right? And I think when I do that, I'll have a clearer idea of what's going on. So let's see. So if x equals y squared, then in order to solve for y, I would take the square root of both sides. And so I'm going to get y equals plus or minus square root of x. So the positive square root of x is the top half of the graph, and the negative square root of x is the bottom half of the graph. So really, I do kind of have two different functions. What I'm going to do is, to find the area between the top part and the bottom part, I'm going to do square root of x minus negative square root of x. Well, that's just 2 times the square root of x, and that makes sense, right? Because let's say that I just integrated from, if I just integrated the square root of x, then that would give me the top half here. That would give me this little top part. And this is symmetric, so if I just double that, then I should get this bottom part too, if I just double it. Well, that's exactly the same thing. So just doubling this top area is exactly the same thing as doing square root of x minus negative square root of x, because then I just get 2 times the square root of x. Okay, so however you look at it, I think we've got the idea. So I'm going to integrate from 0 to 1, right? 0 to 1. I'm going to do root x minus negative root x. Or in other words, 2 root x. Or if you prefer, you could think of it like 2 times the integral of root x dx. And each one of these should make sense. You know, that's the way that we're going to calculate that. So I'm going to do this for this first little chunk, and then for the second chunk, I'm just going to do square root of x, okay, square root of x minus, what was this? X minus 2. So square root of x minus 2. So in total, what I'm going to have is this. So the area is going to be 2 times the integral from 0 to 1 of square root of x dx plus the integral from 1 to 1, 2, 3, 4. So from 1 to 4, right? So from 1 to 4 of root x minus x minus 2. So root x minus x minus 2. When you subtract the bottom function, make sure that you subtract the entire function, right? So you've got to have those parentheses there. That's going to change the sign of the negative 2. It's going to become a positive 2, right? Okay, so what do we get? We have 2 times the integral from 0 to 1 of root x dx plus the integral from 1 to 4 of root x minus x plus 2 dx. Okay, now remember, root x is just x to the 1/2 power. Okay, so we can use the power rule on that. Add 1 to the exponent, get 3/2, and then divide by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So we're going to get 2 times 2/3 x to the 3/2, evaluated from 0 to 1, plus, well, we're going to have the same thing here, 2/3 times x to the 3/2. Here we're going to get x squared over 2, and here we're going to have 2x, evaluated from 1 to 4. Okay, the rest is arithmetic, right? So here, if we plug in 1, we're going to get 2/3. If we plug in 0, we're going to get 0. Here, if we plug in 4, square root of 4 is 2, and 2 cubed is 8. Then 8 times 2 is 16. So we've got 16/3. If we plug in 4, we're going to get 4 squared is 16. 16 divided by 2 is 8, so minus 8. And then if we plug in 4 here, we're going to get 2 times 4, which is another 8, so plus 8. That's interesting. Minus, when we plug in 1, we get 2/3, negative 1/2, and 2. Okay, so let's see. This is going to be 4/3. The 8 and the 8 are gone, so we're going to add 16/3. And here, what are we going to have? 2/3. So we've got 2/3 minus 1/2. That's 4/6 minus 3/6. So that's 1/6. And then 1/6 plus 2. 2 is, 12/6. So 1/6 plus 12/6 would be 13/6. It's so hard to say that word, but 13/6. Okay, I'm going to punch this into my calculator, see what we get. 4/3 plus 16/3 minus 13/6 is 9/2. Right, 4.5. Okay, so that's if we integrate with respect to x. Now, what if we integrate with respect to y? What would that look like? So integrating with respect to y. So instead of thinking of it like top to bottom, we're going to think of it like right to left. You could almost think of it like if you just took the picture and tipped it over. Right? Now what do we want to do? Well, we're going to want to integrate from negative 2 to positive, not to positive 2, to positive 1, right? We're going to want to integrate from negative 2 to positive 1. And we're going to want to do this function, which we're calling y equals x minus 2, but we have to rewrite that. But we're going to want to do this function minus this function. So it's a little bit more straightforward if you kind of tip it over on its side, right? It's a little bit more straightforward. So we're going to integrate from, oh, I kind of led you astray, I think, because I said from negative 2 to 1, but it's the other way around, isn't it? It's actually from negative 1 to 2, from negative 1 to 2. So we're going to want to integrate from negative 1 to positive 2. And we're going to want to do this function minus this function. This function is y equals x minus 2 if you're writing it in terms of x. But if we're going to integrate with respect to y, we need to rewrite this function in terms of y. So y equals x minus 2 would imply that x equals y plus 2. So we're going to want to do y plus 2 minus y squared. Right? This one is already written in terms of y, so we would do y plus 2 minus y squared. dy. Okay? That's a little bit more straightforward, I would say. Let's see what we get. Hopefully the same thing, right? If we don't get the same thing, then something went wrong somewhere. And that's okay. We can kind of troubleshoot together if that's the case. Okay, so we're going to have negative y cubed over 3 plus y squared over 2 plus 2y evaluated from negative 1 to 2. If we plug in 2, we're going to get 2 cubed is 8, so we get negative 8 thirds plus 2 squared is 4 divided by 2 is 2 plus 2 times 2 is 4. If we plug in negative 1, negative 1 cubed is negative 1. This negative will make it a positive, so we get 1/3 plus 1/2 minus 2. Okay, 2 plus 4 is 6. 6 would be 18 thirds. 18 thirds minus 8 thirds is 10 thirds. And here we have 1/3 plus 1/2. 1/3 would be 2/6. 1/2 would be 3/6, so we get 5/6. But then minus 2. 2 would be 12/6. So 5/6 minus 12/6 would be negative 7/6. Is that right? But then this negative makes it a positive, so we're going to say plus 7/6. And then this would be 26. 20 plus 7 is 27, so we get 27/6. We can reduce that by 3. If we divide by 3, we get 9/2. Sure enough. Okay. As you can see, integrating with respect to y in this case was easier. It was an easier setup. It was less kind of nasty work that we had to do. So integrating with respect to y is nice. Especially, like in this case, we happened to have functions that we could solve. Like it's like I could solve this one for y and I could solve this one for x pretty easily. But sometimes you have functions that are not easy to solve for x or y, and so it's nice to be able to sort of go back and forth and integrate with respect to x when it's easier to do so, or integrate with respect to y when it's easier to do that. So that's all I have to say as far as examples are concerned. Just a few things to note to sort of close out our discussion of this section. So always helpful to draw a picture. You should draw a picture every time you're doing a problem like this. It'll just help you to get your bearings. So draw a picture. That would be the first thing I would do. Sometimes you have to do some algebra to figure out where things intersect, okay? So just, inure yourself to the fact that you're going to have to do some algebra to figure out where things intersect. The big takeaway is that when you're integrating with respect to x, the functions have to be expressed in terms of x. You have to have it as y equals some function of x, right? And the limits of integration are along the x-axis, right? They're on the x-axis. When you're integrating with respect to y, the functions have to be expressed in terms of y. You have to have them as x equals some function of y, okay? And then the limits of integration have to be along the y-axis. And you can see that here. When we integrated with respect to x, we had to take both of our functions and make sure that they said y equals some function of x. And then our limits of integration we were looking for along the x-axis. So we went 0 to 1 for the first chunk, and then 1 to 4 for the second chunk, right? 0 to 1, 1 to 4. When we integrated with respect to y, we had to make sure that everything was in terms of y. So we had to solve this function for x, so that we had x equals some function in y. And then the limits of integration we were looking for were along the y-axis, -1 to 2, right? So that's kind of the big takeaway of this section. And that's all I have to say.